friends, in this video we are going to see how a transformer is look like if I am not loading it. That means if I am not providing any load at the secondary side. From this we will be seeing how the equivalent circuit of a transformer will look like and phasor diagram of that. So I will draw this transformer structure once again. So it's a core. This is primary winding because I am giving supply to this coil. And this is secondary winding. Right now it is not loaded. So it's an open end. This is primary voltage V1, which will give rise to a primary current I1. This primary current I1 is flowing through this winding, which will give rise to magnetic flux, which will pass through this core. This direction of flux can be determined by right hand thumb rule. It says hold the winding such a way that curl finger will represent the direction of current, then outstretched thumb will give you direction of flux. So this will be the direction of flux phi. Now this flux phi is linked with this winding having N1 turns, will give rise to EMF E1. Maximum flux will pass through this core, but some amount of flux is complete its path outside the core, which we call as a leakage flux. Now same flux phi is linked with this winding, and here also some amount of flux is going to be wasted in air like this. And maximum part of the flux will linked with this winding having N2 number of turns, which will give rise to EMF E2. Now I am keeping this winding open circuited, hence current flowing over here I2 equal to 0, because of which voltage, which we call as the terminal voltage V2, is same as secondary side induced EMF E2. So this is what happening at no load. There will be I1 current. The job of I1 current is like this. So this I1 I will call as no load primary current. I0, very small value. This I0 serve two purposes, or you can say it has two components. First component, so I0 has two components. If you see properly, there are two things happening over here. One is magnetic flux is getting generated and which is passing through this core, because of which magnetic losses will appear, and those losses are nothing but hysteresis and eddy current. So these are the power losses. So some amount of current and some representation of these losses as a resistance will be there. So current I0 has to serve these core losses, or you can say these iron losses. And secondly, flux phi need to be created. So the job of I0 is generation of magnetic flux, the component which is responsible for generation of magnetic flux is called as magnetizing component. Of I0, we denote it as I mu. Magnetizing component of I0 is responsible for generation of magnetic flux, and second is some amount of current should take care of core losses happening inside the core. So component which is responsible for magnetic losses So what are the magnetic losses happening? Hysteresis and eddy current. Along with the magnetic losses, there will be some primary side copper losses. So the component which is responsible for magnetic losses and primary winding I square R losses is called as core loss component of I0. We denoted it as IC. So core loss component of current is responsible for taking care of losses happening inside the core. Now suppose I want to analyze this circuit further. It is not easy that every time I should have this diagram and then writing all the core, passing through core is a flux, current I1 and all that. So better we can symbolically represent this. So let's check how we are going to write equivalent circuit of a transformer. So I will start from the primary side. So primary side, there are number of turns. So obviously primary side or primary winding resistance will be there, represented as R1. So it will be like this. Now some amount of flux is getting leaked in the air. In account of that, I will represent that as leakage reactance at the primary side. And there are two components always present. One is this magnetizing component, which is responsible for production of magnetic flux phi, and second component is this core loss component, which will serve losses at no load, or even if a transformer is loaded, these two parts will always be there because we need a magnetic flux, and because of that losses will be occurring. So these two parts can be represented in a transformer like this. So this is the primary side of a transformer. Why it is called as primary? Because here I am going to connect a supply. Now at the secondary side, I am having this winding where resistance is present and some leakage flux, leakage reactance will be considered. So the secondary side, it will be secondary winding resistance and secondary side leakage reactance. So this is the equivalent circuit diagram at no load. Once again we will see this diagram. This is V1, voltage applied, primary winding resistance, primary winding leakage reactance, core loss resistance, magnetizing reactance. This is no load primary current, core loss component of I0, magnetizing component of I0. Here secondary winding resistance, secondary winding leakage reactance, N1 number of primary turns, N2 number of secondary turns, E1 primary side induced EMF, E2 secondary side induced EMF. Right now I2 is a secondary current which is 0, and V2 is the terminal voltage of a transformer. So let's list out all this. V1 primary voltage, R1 primary winding resistance, X1 primary leakage reactance, I0 is no load primary current, IC, it is a core loss component of I0, I mu, it is magnetizing component of I0, RC, core loss resistance, XM, magnetizing reactance, E1 is primary induced EMF, N1 number of primary winding turns, R2 secondary winding resistance, X2 secondary leakage reactance, N2 number of secondary winding turns, E2 secondary induced EMF, and finally V2 is the terminal voltage or secondary voltage. Now this is the equivalent circuit diagram of a transformer at no load. Let's draw its phasor diagram. So I will start with flux phi. This flux phi is responsible for production of E1 and E2 primary side and secondary side induced EMF. which will lag phi by 90 degree, that we have seen already while deriving EMF equation of a transformer. So E1 and E2 will be like this. I will consider N1 number of turns are less than that of a N2, hence E1 is less than E2. Now this flux phi is produced because of I mu. So I mu is nothing but magnetizing component of I0. So the current which is responsible for production of flux phi will come in phase with flux phi. So this is I mu. I mu is the current passing through this inductor whose voltage will be E1. Actually, by Lenz's law, it should be minus E1, that we have already seen. So what we want over here, E1 and its opposite phasor is required, which is minus E1. So equal and opposite to this E1 will be minus E1, which will be like this. Now this minus E1 is the voltage across this resistance RC. So IC will be in phase with minus E1, because for a pure resistance voltage and current are in phase. So this will be IC, and we have seen over here I0 is the no load primary current, which is nothing but addition of IC and I mu. Obviously it's a phasor addition. So if I add IC and I mu, I will get current I0 like this. Which is no load primary current. So no load primary current will pass through these two elements R1 and X1. So if it is passed through R1, it will give rise to a voltage drop I0 R1 in phase or parallel to I0. So parallel to I0, I will draw a vector from tip of minus E1 like this. Same current I0 will be passing through this X1, giving rise to a voltage drop I0 X1, which will be 90 degree leading for this phasor. So 90 degree leading will be like this. So this is 90 degree. Now if you see properly this circuit, phasor addition of minus E1, I0 X1 and I0 R1 will be nothing but primary voltage V1. So phasor addition of minus E1, I0 R1, I0 X1 will be nothing but this voltage. Which is primary voltage V1. So V1 is the primary voltage and I0 is no load primary current angle between them is phi 0, no load phase angle. So here we develop a phasor diagram based on equivalent circuit of a transformer at no load. This is required because in subsequent videos we are going to see phasor diagrams of a transformer when it is loaded. At that time, as I said earlier, whether transformer is loaded or not, this part of equivalent circuit will always be there. because we need to produce a flux, and if flux is getting produced, there will be core losses happening. Hence, we always get this part of equivalent circuit diagram of a transformer, whether it is loaded or not. Thank you.